Today we're going to be solving this problem. It is a problem about sequences, and I hesitate to call it difficult because sequences is just an easy topic as a whole, but this problem is trying really hard to be difficult because the problem is definitely more than plug three numbers into a formula and tell me what the fourth number is, which is generally how sequences problems go, right? You have a formula that involves 1, 2, 3, 4 variables. You know three of them, and then you just plug everything in here and find the value of the fourth. This problem is going to require you to do a little bit more than that because it doesn't give you much. You know that there is an arithmetic sequence and a geometric sequence involved, but the only thing he says is that the common ratio is R and the common difference is D, which honestly is not saying anything at all. Now, the same first two terms is saying something. We can begin trying to set up our sequences. I don't know anything about these numbers, so I'm just calling them X and Y, but I do know that it's the same X and Y here in the beginning of the arithmetic sequence and the same X and Y here in the beginning of the geometric sequence. And then he says that the third terms of the geometric and arithmetic sequences are in the ratio 2 to 1. So it is the geometric and arithmetic 2 to 1, which means that the geometric is the bigger one. So I put a z there and a 2z here because the ratio is 2 to 1. So this one is twice as much as that one. And that's it. That's all of the information. He wants us to find the value of R, and then he says to find the ratio of the fourth terms. Now, part A is using values in plural to suggest that there is more than one possible answer, and part B carries on with that hint when it says for each one of the values of R found in part A. So I am expecting to find at least two. But notice that I don't have anything here. The only number that I have is 2 that appears here. And even that is only appearing as double something else. It's not the number 2 itself. The question is not even asking for the value of the fourth term. It's only asking for the ratio between one fourth term and the other fourth term. So there aren't a lot of numbers in this problem. He does imply that the R will be found as a number. It will not be in terms of any other variable in the problem. But it's okay if you find that a little bit hard to believe right now because there are no numbers. So it's a weird problem. It's not an immediate path towards the solution. And let me tell you the way that I approach these things. I am not worried about knowing the path to the solution. I am only worried about knowing what I can do next. What is the first thing that I can do? And that's usually very obvious things. So I am going to write down obvious things about this, such as x plus d equals y. D is the common difference. So that's an obvious sentence. I am going to write as many obvious sentences as I can think of. Sometimes when I do this, I just end up with a bunch of equations and a bunch of variables, and I am so lucky that the number of equations matches the number of variables. The whole thing just turns into a system, and then I can solve and find everything. But that's not really happening this time. I have 4 equations, which were the 4 obvious things to write down, but I have more than that many variables. I have x, y, z, d, and r, so I have 5 variables. Sometimes that indicates that I just forgot to write something down. There is another obvious thing that I haven't seen yet, so there is an equation missing that will make it 5 and 5, but that is not the case in this problem. Some people like to go, instead of x plus d is y and y plus d is z, they like to go straight from x to z, like x plus 2d equals z. And that might be a useful sentence to have in the process of solving the problem, but it's not a fifth equation. It's not a fifth equation because it is just coming from this and this one put together. If you take the y from this equation and you substitute it by this y, which is x plus d, then you get x plus d, which is x plus 2d, equals z. So that is not new information. That was already written down here. And the same can be said for that one, which also could be convenient, but it's not one more equation. We still just have 4 equations. And like I said, sometimes when you have fewer equations and variables in your problem, sometimes that means that you forgot to write something down. There's something that you haven't seen yet. And other times, that just means that your problem does have a degree of freedom. So before we continue, there's just a little something that I want to show you. We can use a spreadsheet to explore kind of how these sequences would work. So I don't really know a lot about the sequences. I don't know any of their terms. So I'm just going to put some random numbers here, 1 and 2 for the arithmetic sequence. And I know that the geometric sequence needs to start with the same two terms. But instead of just typing 1 and 2 again here, because I don't know if 1 and 2 is going to work, I want to be able to change these numbers later. So for the geometric sequence, I'm just going to say that this is equal to cell A2, and this one is equal to cell A3. Because then if I want to change it later, I can just change one of them and the other one will change automatically. But let's leave it as 1 and 2 for now. So for the next term of the sequence, I can say that it is the previous cell, A3, plus the common difference, right? I just want to say that the common difference is A3 minus A2. And that is going to give me the next term. I can copy that to a few more terms. So there you go. It is an arithmetic sequence. And if I do change it here, then everything else changes accordingly. So I can have any arithmetic sequence that I want here, okay? Let's just keep it as 1 and 2 for now, and do the same for the geometric sequence. So this one is going to be cell B3 times the common ratio, but the common ratio is the 2 divided by the 1, right? So cell B3 over cell B2. That is going to give me 4 right now, which is the next term in this geometric sequence, and then I can copy that for a few more terms. Again, if I change anything here, everything else changes accordingly the way that it's supposed to do. And the other thing that the problem is interested in is the ratio between the terms of the geometric and the arithmetic sequence. So I can put that here as B2 over A2, and then copy that to the other cells. Obviously, these two numbers are going to be 1 because the first and second terms are the same in both of the sequences. But this one here, he wanted to be 2. This is kind of the only information that the question gave me. This 1.33 is wrong. It's supposed to be 2. So what I'm going to do now is that I'm going to change these random numbers 1 and 2 that I originally picked. I'm going to change them until I see a 2 in that cell. So what if it was 1 and 3? Oh, then it would be 1.80 instead of 1.33. 1 and 4 is a little too much, so let's try 1 and 3.5. That is still a tiny little bit too much, so I'm going to make this one a little bit smaller. And just by trial and error, I end up finding that 3.41 gives us the 2 that we wanted. Of course, this is not exact, okay? If I ask the spreadsheet to give me more digits here, I can see that it's not exactly 2. But that's not a problem. I'm only trying to illustrate something for you here. And by the way, aside from the number of digits and the precision and stuff, 4.82 is already the answer to the question, right? It is the ratio between the fourth terms of the geometric and the arithmetic sequence. But that's not exactly what I wanted to show you. I wanted to show you that this sequence that starts with 1 and 3.41 is not the only way to get the 2 over there. If I change this to 2 and 6.82, which is everything is just twice as much, then I still have the 2 over there and the same 4.82 here. It really doesn't matter if it was 2 and 682 or 1 and 341. The answer of the problem is still going to be 4.82. So it's not always the case that you are able to find all of the missing information. And I just thought it would be nice to show you that so that you feel comfortable with this notion before being worried at the system of equations that you're not being able to find all of the variables. That's fine. We're not going to find all of the variables, just the one that we want. And that degree of freedom is what makes this problem interesting, because you don't get to just solve a system of equations and find the values of all the variables, then check which one the question was asking for and just answer it. That is not what this problem expects of you. You don't get to just completely solve the system of equations, but you do have to figure out what are the interesting equations to put together so that you can answer the question that he's asking, which is also not just any question. He knows where the freedom is. He knows what he is able to ask and what he isn't. As we've just seen in the spreadsheet, he wouldn't be able to ask what is the first term of the sequence, because there is no one answer for that. Any number could be the first term of the sequences. That is the degree of freedom. But the other things, apparently he can ask. So he's asking me for R. So yeah, our job here now is to keep putting equations together like we were doing. We put these two together to get that. We can keep doing that until we find something that will eliminate variables in just the right way to get us the value of R. We can do that at random if we don't have a plan, if we don't see a path towards the answer now. And I do think that this is good practice. So if you care enough to do that, you should pause the video now and start putting equations together at random just to see where you get. Like, we've done this one with this one and we got there, but what happens if we put this one and this one together? Now we have that x plus d is equal to x times r, because both of those things were equal to y. And if we want an equation that doesn't have the variable y, well, there it is. We have one right here. So you really should do a little bit of that at random before you continue watching the video. And I really can't promise you that the way that I'm going to do it is the most efficient way, the one that gets there faster. It's just the way that I found. Because first of all, I know that I want to find R, so I definitely want to start working with these equations down here that have the R. And I also strongly suspect that there's going to be more than one value of R because of the way that the question was phrased. So I really like this one that has the R squared, because quadratic equations tend to give me more than one possible answer. So I'm going to start right there. I'm going to be trying to get rid of the other variables so that all I have is R, and then I will have an equation in R. It's probably going to be quadratic, and then I can solve it and find two values of R. That is the current plan. And what is currently in the way is the variables x and z. Well, this z is this one, which came from this one. So if I want to eliminate z, I might as well use this one, which is the same as that one, because then I'm mixing up more of the equations. So I'm going to take this z and substitute it for x plus 2d. You could say that this didn't help much, because first I had my r with two extra variables, x and z, and I still have it with two extra variables, which are now x and d. But I do think that it's getting a little bit better, because this x is multiplying here and this x is multiplying here. So I think that if I keep working this way, I might find an equation in which every term is multiplied by x. And that would be really helpful to get things to cancel out. This might just be wishful thinking, but I'm going to keep trying. So what am I going to substitute the d for now? Because I do want to get rid of d. It's an extra variable. And I've just said that I'm okay with x's because I'm hoping that they will disappear on their own. So this is the d that I'm going to use. That d is y minus x. There's a 2x minus 4x here that I can collect the like terms, right? But now I still have the y. I want to get rid of the y. It's an extra variable. I don't want it to be here. The variables that I want to be here are the r, which is the one that I'm trying to find, and the x, which I'm kind of okay with. So look at this. Y is equal to r times x. That is exactly what I wanted, because now I can divide both sides of this equation by x, and it has become a quadratic equation, which is something that it is easy to solve. I'm just going to put that into the quadratic formula, which is giving us 2 plus or minus the square root of 2 as the possible values of r. And remember the example that we were finding in the spreadsheet? This was the example 1 and 3.41. Which means that when you look at it as the arithmetic sequence, it's adding 2.41. But when you look at it as the geometric sequence, it is multiplying by 3.41, which is 2 plus the square root of 2, approximately, because that's what we were doing in the spreadsheet, and the square root of 2 is approximately 1.41. But now we have to look at the fourth terms of the sequences, what goes here and what goes here. Well, this is just 2z times r, for one of these two values of r that we just found, but that one is z plus d. And we still don't know anything about d. We're going to have to go back to our equations to find out something. We kind of said something like that a while ago. When we put this equation together with this one, we get x plus d equals x times r. But maybe that's not the way that I want to do it, because x is too far away from the fourth term. Z is closer. So let's see if we can do something with z instead. Y plus d equals z. And I don't like that the y is here. I want z. So I can use this equation to get rid of the y. Y is going to be equal to 2z over r. So now I'm just isolating d in this equation and getting it in terms of z and r, which is really useful because now I can use it to write down the fourth term of the arithmetic sequence in that way. And the question just wanted the ratio between the two fourth terms. Let's write that down. I've factored out the z from the fourth term of the arithmetic sequence, okay? Because I wanted to show you that this cancels out with this. This is the degree of freedom going away. And now I can just simplify this whole thing. 1 plus 1 is 2. I'm also putting it in the same denominator as the other fraction so that I can add them up. That division by r in the denominator became another r on the numerator. Now I'm going to divide the numerator and denominator by 2. And now I'm going to plug in both of the possible values for r. That is going to give me exactly what letter B of the question wanted, which was a ratio for each value of r. I don't necessarily recommend that you try to do them both at the same time with the plus and minus like this. It may be a good idea to write them separately, one of them just with the plus and the other one just with the minus. But it's also interesting to do them together and see what kind of issues comes up. So I'm going to do it this way. First of all, I'm going to expand this special product on the top here, just being careful that one of them is going to be plus and the other one's going to be minus. But it's only the middle term that has the plus and minus. The other two are always positive. 4 plus 2 is 6. And now I want to rationalize the denominator, which is really when it becomes tricky, because I need to multiply by this with the opposite sign. But the opposite of plus is minus, and the opposite of minus is plus. So I'm writing it upside down like that, with a minus plus instead of a plus minus. And I know that it's unusual, but it is correct. In fact, more than just being correct, it has meaning. It means that when this is a plus, that is a minus. You can't take the top sign from here with the bottom sign from there, for example. You have to always be doing the top ones or always be doing the bottom ones. And when you multiply this by that, well, the rationalization is going to work either way. The denominator is going to be 1 minus 2. But when you do the distributive to multiply the numerators, then you're going to have to be careful with the signs, because this plus is always going to be going with that minus, and this minus is always going to be going with that plus. So 6 times 1 is just 6, but 6 times minus plus root 2 is minus plus 6 root 2. Now when I take the plus minus 4 root 2 times the 1, then it's a plus minus down here. And the 4 root 2 times the root 2, well, that's 4 times 2 is 8, but it's either plus times minus or minus times plus. So either way, that 8 is negative. And now I want to collect the like terms here with the root 2's. So it's minus 6 plus 4, which is minus 2, or plus 6 minus 4, which is 2. So it's always 2, but it takes the sign of the 6, which is the bigger one. And then obviously 6 minus 8 is just negative 2. The denominator is negative 1. And I think it's just going to look better if we change all the signs now, multiply the top and the bottom by negative 1 so that we don't have this denominator. So those are the possible ratios between the fourth terms of the geometric and the arithmetic sequence. The one with the plus is the one that happens when the ratio is 2 plus root 2. And the one with the minus is the one that happens when the ratio is 2 minus root 2. So the one that we were finding in our example in the spreadsheet was the positive one. We've already mentioned that the ratio was 3.41, which is the positive one here. And if you take the plus value here, 2 times 1.41 is 2.82. plus 2 is 4.82, which is the ratio between the fourth terms that we were finding in the spreadsheet. And the thing is that we changed the values in the spreadsheet and we were still finding the same values. So if you're wondering where the other one is, why we never found in the spreadsheet something with a ratio of 2 minus root 2, it was just lack of creativity when I was sitting on the computer, because 2 minus root 2 is something like 0.6. It is a number that's smaller than 1. So that would make a decreasing sequence. And I was only looking for examples of increasing sequences. The other interesting thing that happens is that when the sequence is decreasing, the arithmetic one is eventually going to go negative. It's going to have negative terms because it started somewhere and then it's subtracting a common difference. Eventually, the terms are going to be negative, which is good because the ratio of the fourth terms in that case is going to be a negative number. 2 minus 2 root 2 is a negative number. So you can go ahead and look for examples like that if you want. The moral of the story is that there's only two different kinds of examples that you're going to find, the increasing ones and the decreasing ones. There's not going to be any middle ground. It's going to be one type or the other type with this one or this one ratio between the fourth terms. But if you stick to one of those types, like I was doing in my spreadsheet, I was always having to multiply everything by a number. So instead of 1 and 3, it was 2 and 6. Notice that that keeps the same R for the geometric sequence, but it changes the D for the arithmetic sequence. So it is a good thing that the problem was asking us in part A for the common ratio. It was not asking us for the common difference, because we could not answer that question. The common difference is not always the same. So why is it that one of them we can find a concrete number for and the other one we can't? Well, this has to do with the fact that the restrictions that were given were in terms of ratios. The ratio between the third term of one and the third term of the other was 2. And then he was asking for the ratio between the fourth terms. So that is a multiplicative thing, which is why it's going to work better for the geometric sequence than the arithmetic sequence.